Hello class, this is a video lecture all about how to graph and doing things with that graph. You're going to do this on page 17 of your interactive notebook, which will be a page on the right hand side. It'll be right after the notes we took about the close reading article. Alright, now that we're all looking at our page 17, or at least you should be, let's begin. The benefit to a video lecture like this is that if I'm going too fast, you can always pause, rewind, and listen to that part again. This is what I expect you all to do, which means I'm going to be going kind of fast, because you can pause, and so on. Away we go. Alright, now, here is a basic graph. Let's talk about what the different parts are called. Well, let's talk first about the axis. There's my vertical axis. Vertical because it's going up and down. Horizontal because it's going horizontal, like the horizon is horizontal. Now these two axes can be different things, but in physics, the horizontal axis is always time. And there it is labeled. And there's that one labeled. Now this is an xt graph, which means it's position over time graph. Once you have your axis set up, you can plot your data points. And once you have all your data points, you can draw your best fit line. Alright, now that we have all that, moving on. Bam! Now, as I have said, your horizontal axis should always be time. And we measure time in seconds. Always. Now that vertical axis could be a few different things, but in this class, it's going to be position, in which case it's measured in meters, or it's going to be velocity, in which case it's measured in meters per second. When you label your axis, you've got to say what it is, so x, t, or v, and you have to say what the units are. So far, all of you know how to do all of that, and you did all of this correctly on the test. Here's the part where people started messing up. Every graph has a scale, which is how much one box is worth. Sometimes one box is 1 second, or 1 meter, or whatever. But usually, it's not. Usually, one box is not 1 second. For instance, you could have one box be half a second, or 10 meters. It doesn't really matter. Your scale could be anything. And you always set up your scale so that your graph fills the entire page, the entire graphing area. You never make me a graph that takes just a tiny little piece. For instance, what a lot of you did, if that was your graph paper, you guys made a graph that was that big. I don't want that. I want a graph to take up the entire room. Alright, so here I have an example set of axes. Now see that here on time, on the horizontal axis, see how one box is half a second? It takes 2 boxes to get to 1 second. And then over here, it's still 2 boxes to go a second. Each box everywhere on the axis is worth the same amount. Now let's look at the vertical axis. 1 box is 10 meters. And if I go anywhere else, 1 box is still 10 meters. Now this seems obvious, but what a lot of you did is you just put whatever numbers that I gave you down instead of 1, 2, 3, 4, 5 seconds and 10, 30, 50, 70 meters. You put exactly what I gave you. And that just gave you a line that looked like that, when that's wrong. So, now that you've set up your axes, how do you plot your data points? Well, if here I have my data points, I have 1.5 seconds, 2 seconds, 3.5 seconds, and 4 seconds. I have to make sure that my axes are not just the numbers that I gave you. See how that the time is not 1.52, 3.54, how it's 1, 2, 3, 4, 5, and how the position is 20, 35, 55, 70, but on my axis it's every 10. That's how I want it. So now that I have my axes set up, and I know what my data is, for each data point I'm going to read the time and position, so 1.5 seconds in 20 meters. Then I'm going to go over to that time on the axis. Then I'm going to go up to that position and make a dot. For instance, 1.5 seconds, 20 meters. 1.5 seconds, okay, that's there-ish. And 20 meters, okay, that's going to be there-ish. So I'm going to go over to 1.5 and then up to 20 and make a dot. Next one, 2 seconds and 35 meters. So I'm going to go over 2 seconds, go up to 35. Okay, well there's 30. The next line is 40, so I want to go in between those two lines to get 35. 3.5 seconds and 55 meters. All right, so 3, one line over gives me 3.5. Go up to the 50 mark, and then half a box more. That's a little high. Oh well, close enough. And last, 4 seconds and 70 meters. All right, so over to the 4 line, up to the 70 line, and make a dot. And there I go. I have my data points plotted. Now, whenever we make a graph, the very next thing we need to do is make a best fit line. A best fit line is a line, or sometimes a curve, that goes right through the middle of your data, and it tells you what's going on. Now, your best fit line does not have to go through 0, 0. Literally every single one of you made your best fit line on the test start at 0, 0. It does not need to do that. It also does not need to connect all the dots. In fact, you don't want it to, but some of you did. For instance, here's my graph. Here's how to do it wrong. Connect the dots. No, don't do it like that. All right, well, what about this, Mr. Sasley, you might say? What about if I put it right there through 0, 0? No, also wrong. What you want to do is you want to look at the actual points. I want my line to go through as many points as possible. Okay, well, I'm going to draw it somewhere there-ish. I know I have a good best fit line when I have the same number of dots above the line as I do below the line. So there I go. There's my best fit line, and it looks pretty good. Now, the really cool thing about my best fit line is I can use it to predict things. For instance, say I want to know where I am at second 3. Well, my data table from before doesn't tell me anything about second 3. I mean, here it is. Look at it. It says something about second 2. It says something about second 3.5. I could do some math, I guess, and figure out where I am at second 3. Or I could use my graph. So, second 3. I'm going to go up to second 3. Oh, look at that. and then I'm going to go over and read off what it says. So even though I don't have a dot there, because I have a best fit line, I can say that at second 3, I was at 50 meters. And that's really helpful. All right, now, something that a lot of us got wrong is how to find the slope of a best fit line. All of you know and did correctly, slope is rise over run. All of you know and did correctly, that means you need to find how far up you go and divide it by how far over you went. Here's where people did things wrong, though. Lots of you didn't use your scale. You counted the number of boxes. Don't do that. Instead, you need to use the numbers on the axis. You need to use your scale. The other thing that people did wrong is you used your data points instead of the best fit line. This is the slope of your best fit line, so you really do need to use the line and not your data points. Some examples. So here I have my graph. I have chosen 2 points, and I find out how far up I go, 35 meters, and I found out how far over I go, 2 seconds. Find my slope is 17.5. Wrong. Why? Well, because I used 2 data points and not the best fit line, where what I want is the slope of the best fit line. Here's another one. All right, I'm not using data points now. I'm using the line. I'm going up 4 and over 4 for a slope of 1. Wrong. Why? Because I counted the boxes and not how many meters I went up and how many seconds I went over. All right, so same thing. But now I'm saying, okay, well, I go up 40 meters. I go over 2 seconds for a slope of 20. Correct. Now see the big difference? We started with a slope of 17.5. That's close, but it's not right. The second wrong way, we got a slope of 1. That's really wrong. You have to use the line, and you have to use the scale to get the correct slope. But, you might ask, why do we even care about the slope, Mr. Saslow? Well, you may recall from notes that on a position time graph, the slope is the rise over the run, so it's the change in the vertical over the change in the horizontal. Vertical is your x, so it's your change in x. And horizontal is t, so it's your change in t. Slope gives you delta x over delta t, which is velocity. And the same thing is true for a velocity time graph. Slope is change in vertical over change in horizontal. But vertical is now v. Horizontal is still t. So now you have slope equals delta v over delta t. On a velocity graph, your best fit line slope gives you the acceleration. All right, I'm done with the video lecture. At this point, you need to go to Echo. You're going to open the activity called Graphing Activity. And in your groups, you're going to follow instructions. Go.